organizers of one of the events here. So I remind that we have two events going on at the same time. One is about random matrices and multifractality in condensed matter. Another one is about Weyl fermions in condensed matter. So today here, the two events meet. So it's a joint event also for people here at the Institute. And thank you very much for coming. And I pass the word to Fyodor Kuzmartsev, who is one of the organizers of the Weyl fermions event. So he will present the speaker.
Okay, thank you very much. It's actually it's a great pleasure for me and honor to present a distinguished speaker today, and Zahid Hasan, who is a Eugene Higgins professor of Princeton University. So he came from Bangladesh. He studied in Bangladesh high education, and then he's studied in Eastern University quantum gravity theoretical project, considering linearized Einstein equations, some first loop corrections, diagram techniques, so a very successful project under Steven Weinberg. And then he asked Steven Weinberg what to choose, and Steven Weinberg told him that now it's most excited area in condensed matter physics. It's emerging phenomena, high TC materials, novel materials, quantum Hall effect. So he decided to move to Stanford to study high energy experimental in SLAC and accelerated center, and he has idea to develop new method based on momentum X-ray resonance scattering, which helps to investigate the band structure, so different properties of the band structure. So it was some kind of complementary method to X-ray photoemission spectroscopy, neutron scattering, resonant neutron scattering, elastic neutron scattering. And he was very successful in this, developing new method, new beamline. It was joined between Berkeley and Stanford. So then after that, he got some postdoctoral fellowship, distinguished Robert Dickey Fellowship in Princeton, but it was not very long. After one semester, he got faculty position in Princeton and started his research laboratory, right? And developed research laboratory, which he is doing simultaneously both theory and experiments, right? So in some sense, it's STM what he's doing, MBE, molecular beam epitaxy. So then ARPES for the emission types, he can do samples in situ MBI, immediately check them. And at the same time, he's doing many-body DFT, which is complementary different correlation function, response function, which people do the same time simultaneously for this material to get properties of this material and to find what is most interesting, helps to understand physics. So and now he's already 70 years in Princeton and has office neighboring to Phil Anderson, Duncan Haldane. And so he has a lot of continuing conversation and influence of these people. And he made most distinguished discoveries in condensed matter physics and was named as the most influential mind in physics for 10, some kind of breakthrough in physics. So I can, very difficult to list all his discoveries in topological materials, in Weyl semimetals. So it's just, it's a very long list. His prizes, he was in Loughborough, give Mott lecture. That's what we can do from our side to contribute his prizes. And so he has more than 40,000 citations. He has plenty of students. One of his students is already full professor in Caltech, another one in Harvard. So it's a lot of interesting stuff going on around. So it's a great pleasure to have him here. So so that's why I would like to give these words. He will tell us about latest discoveries about these exciting directions, which I dedicated our program of these Weyl fermions and condensed matter. And so when he is participating in this as well. So then he will give today one lecture, tomorrow will be another one from 1:30 in the same office. So it was some kind of joint from both programs, so everybody welcome. So we have serious lectures already whole week. was excited, and that's more or less. If anything forgotten, please, I'm sure you will tell it. Please, Professor. Thank you very much.
Thank you. I think this is good enough. Yeah. Thank you. I mean, thank you for a nice introduction. I did not know. I mean, I did all that thing, but yeah, it's exciting. I mean, there's a lot of interesting physics happening in last 10, 20 years. Okay, so I am certainly not going to talk all that. We will talk about what I have done, but this particular talk will focus on topological materials, especially how topological insulators gave rise to Weyl semimetals, and so that particular path. And also, this is not meant to be a in-depth theory talk. It's mostly about how these concepts, theory concepts, were realized in real materials. So I'll mention theory only in that context, in the context of experiments. And in terms of experiments, I'll also not be talking a lot about transport. I'll talk a little bit transport, but mostly spectroscopy, where the effects, the topological effects, have been, at least so far, most clear. Okay, so that's sort of the setting of the talk. And so if you think like some 20 years back, if you're teaching, or maybe even 10 years back, you're teaching condensed matter physics, you tell that it's about metals, insulators, superconductors, magnets, and their phase transitions among these states of matter. And say Kittel's book or Ashcroft-Marmin book, you'll find a quantum mechanical description of these states of matter. And each of these are distinct states of matter. But what is the surprising thing, or the excitement in condensed matter, is that in last 10 years or so, theorists and experimentalists working together have discovered a number of phases of matter that are not those phases don't fit into any of these categories. And so this talk is mostly about that, how or why they don't fit into this category. So with this initial slide, I'll just mention one example, topological insulator, for example. So topological insulators are conducting on the surface and insulating in the bulk, but this is not an accident of surface chemistry. No matter how you chop the bulk, as soon as you open up a boundary, a surface, it will be conducting. So you cannot, it's neither a fully conductor or fully insulator, right? So there must be, whereas a band insulator that you learn in a textbook scenario, a band insulator can always, not only it's in the bulk, it's also, you can make the surface insulating at the same time, and it doesn't, you can choose the surface without deforming the state. You can have a surface insulator and bulk insulator, but here your bulk is insulating, the surface is conducting, and it's not an accident of choice of surface, okay? So then this classification, so there must be a phase transition between the two. I'll talk about one of these, and that phase transition is telling you that it's a distinct state of matter. Similarly, so with this example, we see that topology, or if you come from a math point of view, topology is, one way to describe topology is consider bulk boundary correspondence. If there is a non-trivial topology in the bulk, its signature will be in the boundary. So the fact that this topological insulator's bulk is non-trivial or distinct from a conventional insulator, it can be seen on the boundary. So this bulk boundary correspondence or bulk boundary distinction can be applied not only to insulators, to many other phases like magnets, semimetals, or superconductors. So that means this classification scheme or this way of thinking about states of matter is broader than that. It goes beyond classifying symmetries or spontaneously broken symmetries. So, so then in last 10 years or so, we have seen topological semimetals, topological magnets, topological superconductors, and a number of other phases of matter. So, so certainly a number of this topological concepts gave rise to a number of novel states of matter that experimentalists have not been either have not been exploring or have not utilized to realize other effects in devices and in other settings. So, so in this talk, I will not have time to talk about all these phases. I will focus on insulators and semimetals, and a little bit of magnet. I'll skip superconductors, although we are doing a lot of that stuff. Okay, so what is kind of the historical origin, how topology entered condensed matter physics? This was highlighted by 2016 Nobel Prize, that quantization of Hall conductivity, this quantum number is actually a topological quantum number, and in the context of the Hall measurements, Hall experiments, it gives you a counter of the edge state. So that's the boundary states. The bulk is insulating, but the boundary is conducting. And this you can and this quantum number it's related to the Berry curvature field of the occupied electron bands. So then, so it's the bulk band structure essentially determining which of the insulating states will have a boundary mode. So why is this experimentally interesting? The original quantum Hall state, or which in modern parlance you can call it topological insulators in 2D, is that this edge state, this edge conduction is a robust property of the system. You can have some degree of disorder or imperfection in the system, but the Hall quantization is extremely precise, and the precision level is like 1 parts in a billion. So that was a very surprising thing when quantum Hall effect was discovered in the 80s. So this precision level is this level of precision is tied to the fact that there is a topological quantum number involved, and this edge state is topologically protected. Okay, so that's the beginning of the fun, and it took a decade or two to realize that this topological quantization or topological effects could be could appear in different disguises or with different types of interaction. So in the quantum Hall physics, you apply a field, and then you create a chiral edge state. You use your right hand or left hand rule, and that gives you a real space picture. Where is the edge current, boundary current, and where is the bulk insulator? So if you take this setting and consider dispersion relations of electrons that are involved and plot that in energy momentum space, you'll see that the bulk bands, there is a gap, band gap, that's why it's insulating, but on the boundary it's conducting, so there is a chiral edge state. So there is K plus state, but there is no K minus analogous state. So in other words, the momentum, energy momentum space or dispersion relation of this electrons in this quantum Hall state is represented here. So this is another way of representing this thing. There is an edge state, edge electron, chiral edge electron moving in one direction. So one can hypothetically think that is it possible that we have counter-propagating edge states? If we have counter-propagating edge states, So here, this chirality is defined by the direction, the fact that you have a magnetic field that gives you the, defines your handedness of the system. This is why it's chiral. And now one could ask that, is it possible to have counter-propagating edge state? So that means you have field up, and then edge states in one direction, and then field down edge state in the other direction. But in that case, your net Hall conductivity, charge Hall conductivity is 0, right? But then one could also think of two copies of integer quantum Hall state, but not through the real magnetic field, but interaction that is already in the electronic band structure, the spin-orbit interaction. Spin-orbit interaction is the relativistic term where there's a dependent magnetic field-like interaction term, right? So then, is it possible that you have spin up going this way or spin down going this way? And is such state topologically protected? You can clearly see that it's not topologically protected by the Chern number, the one I showed. It's got locked somewhere. Yeah. So Chern number is 0 because Hall conductivity is 0, but it may be protected by some other topological invariant. Chern number is not the only topological invariant, and that is the new thing here. So it turns out that you can think of parity of the wave functions, or Chern parity. You can define some sort of parity related topological invariant. So it turns out that was identified by Kane and Melly. There's a Z2 invariant. It's related to the parity of the wave functions. It's not Chern number that's protecting this state. There is another new topological invariant that could protect such a state. Now you can see here, there's two copies of the integer quantum Hall state. This integer quantum Hall state breaks time reversal. Once you have a magnetic field, the time reversal invariance is broken, but here you restore time reversal symmetry, and the Z2 invariant is related to that time reversal symmetry. Now, this crossing, now you can see that the low energy degrees of freedom around this crossing is described by the Dirac equation. So that's how Dirac physics entered topological materials. So it's this thing. Now, you can also think of generalizing this state in 3D, thinking of the integer quantum, thinking of generalizing the integer quantum Hall state in 3D. You would think that you stack them, then you have the chiral edge states, then the edge states become surface states, but that doesn't cover top and bottom, right? So, but then here, the interaction term that is creating these states are spin orbit. So spin orbit, for spin orbit, we're not choosing a direction. So the spin orbit interaction, because of the spin orbit interaction not choosing a direction, we can this can be generalized to 3D. So in other words, all these surfaces, including top and bottom surfaces, one could have a Dirac cone, unpaired Dirac cone states. And then this unpaired states is spin momentum locked. In full theoretical detail, this state is described by 4 invariants. I'm not going to get into that part of it, but you can sort of visualize this from here, that once you create a time reversal state out of this quantum Hall state by considering 2 copies, then you have a Dirac band structure. But then when you consider its generalization in 3D, then on the surface you have a surface Dirac cone. Now that looks like graphene, except that you have reduced degrees of freedom. So this is unpaired Dirac cone. So then physically now if I go back and draw the real space picture, then you have spin up electrons moving in propagating in one direction, the spin down propagating in the other direction, and this is happening in all surfaces. So this is kind of like a real space visualization of this topological state. And it's not tied to the choice of the surface. I can cut it open in some funny direction, and in all directions there will be states like that. In addition, there may be trivial surface states, but these states will be there. And this is because this is determined by the bulk invariance. Okay, so that's kind of a conceptual review without going into the theory. So then next we ask the experimental question: how do we know? How do we detect these states, or how do we probe their property? So there, again, we look at the quantum Hall physics, and we see that these quantum Hall, these topological quantum numbers, they just came directly from transport, because quantum Hall physics was discovered through transport. So it just naturally came out of that. But now with this 3D topological insulators, we're dealing with 4 topological invariants. So how do we experimentally measure this topological invariance? Now, unlike Chern number, these invariants are related to the parities of the function, which is more subtle, and the parity product and all that. And these invariants do not necessarily appear in some response function where it naturally is a prefactor, or it cannot be just directly measured as a response function. Except for the first one, it can be measured in a magnetoelectric as a magnetoelectric quantization of the system, 3D response, magnetoelectric response. But these invariants are not connected to any of those invariants. So now to identify the 3D topological states, we need a technique that can go even deeper than that, more fundamentally sensitive to the electron wave function. So our approach, experimental approach, is to image these electrons in the bulk and the surface in a way that we cover all the degrees of freedom. So electrons have energy, momentum, and spin, and they can be on the surface or they can be on the bulk. So if we can find a technique that can image the electrons with certain details of the wave functions on the bulk and the boundary, then we have a complete handle of the topology, because it doesn't depend on anything else. So that it turns out that, so it turns out that angle resolved photoemission spectroscopy that can achieve that. It's just a modern version of Einstein photoelectric effect done with a powerful X-ray source or laser source, and with highly sensitive detection technique. So, and then including spin sensitivity. So then if we can image all these electrons on the surface and the bulk, and then we can try to put things together, and these images will tell us about this topological invariance. So that's one way of doing it. And now before we move, so we can see that these are parity-based invariants, so they're double valued, 0 or 1. So then you can see that in 3D there are 16 different types of insulators, and one of them all trivial, because if these invariants are 0, 0, 0, 0, then it's a trivial insulator. Silicon is one example, and but then if one of these invariants is non-trivial, say it's non-zero, then we could get a 3D topological insulator. So now you can see that in 3D there should be 15 distinct types of topological insulators, and our goal here is to figure out which one is which. So there are many compounds with strong spin orbit coupling, and by imaging surface and bulk and trying to image these invariants in a direct way, we can tell you which compound is realizing which topological state in 3D. So I'll not give you a lot. I'll give you one example. This is the simplest example that will give you a feel for what it is. So what we are doing here, this is one of the first 3D topological insulators, the bismuth selenide and telluride. In this case, if you look at the bulk band structure, you see it's superimposed on the surface. You see there is a linear crossing. And if you just look at the Fermi surface, then there is a single Fermi surface in the inter-Briand zone. And then each crossing, the Fermi surface, each point on the Fermi surface is singly polarized. And if we do a spin scan, then we see it's polarization down and polarization up with respect to some reference. But what it matters is that polarization is reversing as you go around the Fermi surface. And you can see that if you, this is kind of like half Rashba. In a Rashba case, you have two copies of the Fermi surface, right? So when you have one single copy of the Rashba, you immediately see that now the Berry phase is half of Rashba. In this case, it's pi Berry phase. So there is something non-trivial about it. So then what we do, we not only image these surfaces, we also image the bulk, and then we also image these states by scanning the chemical potential across the gap. So what we see is that no matter who you place the chemical potential in the gap, you always have these surface states. And then their spin texture is reversed as you go through the Dirac node. So this guarantees that you always have odd number of crossing as you count from the center of the zone to the boundary. So then you have a single crossing. And okay, so then why is this interesting? So if we then draw the real space image, that K plus going to the this wave packet to the right is spin down, and this is spin up, and that's all we have on the surface. So now you can see that in a situation like that, you cannot backscatter. So this spin texture is not allowing you to backscatter. So this is one way the 2D surface state, 2D electronic states on the surface of topological materials are distinct from other types of 2D electron gas systems. So this absence of backscattering, you can also see that in STM, and then you can map from ARPES Fermi surface to the STM quasi-particle interference pattern. Okay, so then how do we know that these states exist outside the vacuum? So all these experiments I showed, they're performed under ultra-high vacuum, and the surface is prepared in a special way. So one way to probe that, check that you have surface state is to do transport. Now, if you have sufficiently bulk insulating topological insulators, your transport signal will be mostly coming from the surface, because only surface is conducting. And if the surface is conducting, then you'll see, so it's a 2D electron system, 2D electron gas system. So then you should be able to see the Hall quantization. So in the transport geometry, your both top and bottom surfaces contribute. So then your half integer and half integer add up to an integer. So then if you do transport, you'll see this integer quantum Hall effect. So for that reason, I think when people studied these materials with transport, they never found anything that unusual, because integer quantum Hall is not a new thing. So, but this also highlights why transport is not immediately telling you whether you are working with a topological insulator surface or with a conventional 2D electron system. There are finer checks, but then it gets more complicated. But this, for my purposes, what it is telling us that we're combining that with spectroscopy. We see that on the surface, we have a single Dirac cone. We can count the number of degrees of freedom, and then all these numbers match up. So the primary evidence for topological nature of the surface state is coming from from spectroscopy. You can also do more complicated transport to make a distinction. People are still trying to do many of that stuff. So now, as I said, the integer quantum Hall effect is the first example of topological states in 2D, at least. And experimental point of view, from experimental point of view, much of the quantum Hall physics is happening at low temperature with a high field, right? So what 3D topological insulators and materials brought us, that you have access to topological states without any external magnetic field and up to room temperature. This is one of the early demonstration we had, that these helical Dirac fermions, they survive up to room temperature, and their backscattering is also can be tracked. And then this also allows us to count the density of states in the systems, and then we can show that these are like half Dirac gas. So what is interesting is that now we can see topological effects at room temperature without magnetic field, and that makes the device or application community excited about these things, because you want to operate at room temperature without a field. So that's one of the reasons many people are working on it. So I did not go over all the details of topological surface states. We have worked on some of that stuff, and this is detailed in this review article, including transport that was happening back then. But the key thing to remember is that you have a single Dirac cone, and there is a band inversion in the bulk. So and then the band inversion creates the topological twist. So I will connect that to the Weyl physics. For the rest of the talk, I'll show how tuning a topological insulator can give rise to Weyl semimetal physics. Okay, so before I do that, I should mention that 3D topological insulators can be used to do a whole lot of things. I have only listed things that are more topological, in the sense that can we use topological insulator to create other novel topological states of matter. For example, we can create this Jackie-Rabi type of states, SSH type states, topological magnets, topological superconductors by inducing superconductivity, and then also using that to realize things like SYK. We're working on all of this stuff. So, but here I'll just focus on these two things. They're kind of connected, and also it's a theme of this workshop. But if you're interested how you could use topological insulators to do things like SYK, that's a black hole on a chip idea, I'm happy to chat with you, or more basic stuff like Jackie-Rabi type states. Okay, so from now on, the experiments that I will be talking about are collective efforts of my students and postdocs, Ilya Belopolsky, Guang Bian, Gochin Chang, Jiaxin, Sonia Suyang. Some of them have left the group and found their positions. Suyang is joining Harvard next year, and Guang is in Missouri. And then we have a list of collaborators worldwide. And in this particular talk, I'll talk about data on samples that are taken by Shuang, prepared by Shuang, Shankar, and also Nitin Samarth. And then we also have a grant for doing FP, DFT type of work. There's a list of collaborators here. Okay, so the topological insulator Dirac cone we have seen. If you go back to my second slide, I talked about time reversal symmetry. The one edge, chiral edge state, then you add another one. So that gives you time reversal symmetry, and this is protected by time reversal symmetry. So what happens if we break time reversal symmetry on the surface of a topological insulator? Then the Dirac point is not protected. Okay, so then you will have a gap. So you'll create a massive Dirac fermion, or it's a gapped Dirac state. So there are two ways to create that. One is you dope magnetic impurities in the bulk of the topological insulator, or you deposit magnetic impurities on the surface. And we have done both, and we found that even if the magnetic dopants are not homogeneous, from spectroscopic measurements we can tell that there is almost always there is time reversal symmetry breaking affecting the Dirac cone in momentum space, which is interesting. It's not immediately obvious why that should be so, because we're working in momentum space, K space, why we should see a nice gap, relatively nice gap, when the magnetic magnetic field is not necessarily homogeneous. But this is experimental fact that has been established. Now we can see that there is a gapping behavior here, and the nice Dirac crossing is lost. And this is correlated with the fact that there's a surface magnetization that we can correlate with the presence or absence of hysteresis. Okay? We can do more finer experiments to understand the origin of the gap. I mean, there could be some extrinsic origin of the gap. So what we did is that we doped these topological insulators with non-magnetic impurities and magnetic impurities, and see under what condition you have the Dirac cone is destroyed. So what we found is that if you dope them with magnetic impurities, so then this is example of that, and then measure the spin texture near the band edge, where it looks like there is a gap. So we see that if you have a Dirac cone in the undoped topological insulator, the spin texture is like that. I showed a few scans of that. But here, when you have, even if you have states here, the spin texture is different. For example, if you place your Fermi level here, there's a net moment on the Fermi surface, on the surface Fermi surface, right? That is not the case in the topological insulator that is undoped. And the way the spin texture is disrupted in the doped, magnetically doped case has a characteristic signature. And not only that, it also has a temperature dependence. So that is telling us that it's related to interaction that is involved. So then we did a lot of the systematics that there could also be in a thin film, there could be a tunneling gap. If surfaces talking to each other, it could be a gap. Then we can measure the spin texture and figure out what is the signature of spin texture disruption when the gap is due to tunneling, or when the gap is due to magnetism. So what we find is that when the gap is due to magnetism, if you place your chemical potential here, there's a net moment on the surface. So this is what we call hedgehog spin texture. So that means, and then now we can see that as you move out in energy, then far away in energy, your spin texture is similar to the undoped topological insulator. So in other words, if you place your chemical potential here, it will look like spectroscopically, it will look like there is a pi Berry phase. But whereas if you're up here, then the pi Berry phase is destroyed. So in other words, there's a Berry phase tunability that you can achieve by changing the chemical potential, at least spectroscopically. So this is a signature of a Charn gap insulator. It's a characteristic thing of the Haldane model. So then if this is topological, this magnetic 2D topological magnetic insulator, then there should be an edge state. So now the question is, are we seeing that edge state? So these experiments are done with ARPES. ARPES is not good for looking at the edge state, but it can look at the surface state. So our signature is that this Berry phase tunability and the spin texture. And then later on, people have seen those edge states in both in transport and other scanning probe measurements. We ourselves did not detect the edge state, but it's a Chern gap state. Okay, so then how is this connected to the Weyl physics? So one way to think about it is that what we are doing to create the Chern gap state, we broke time reversal symmetry topological insulator, placed the chemical potential in the gap, and then spectroscopically probe the state. Now, we can also, there's other way of destroying the topological insulator state, or you could also say we start with a trivial state and then generate the topological states through band inversion. So this is what we are doing here. So this is on bismuth based topological insulator where we are tuning sulfur and selenium. Selenium is heavy, it has large orbit. Sulfur has weaker spin orbit. So then when there is stronger spin orbit, we see a topological state by spectroscopic measurement. And then when we go to the sulfur end of it, we see that there's a gap. Otherwise, if it is topological, there would be a Dirac cone here. So in other words, in between there is a transition happening, a band inversion transition happening. If you like, you can call it topological phase transition happening. So the goal, experimental goal, is to detect that state. What is the critical point? Why is this interesting? Because at that point, now, there's a 3D Dirac cone in the bulk, because that's where the band is inverting, right? So we can trace that spectroscopically. This set of images are better. So when you have a trivial band insulator, we see a Dirac gap. On the other end, after the band inversion, we see an indirect gap. And in between, as we increase selenium concentration, at some point we see there is a gap closing. And then by looking at the kz dependence, kx, ky, kz, we tell whether it's a 3D Dirac cone or not. So now you have a 3D Dirac cone. You can locate in these materials or in other related analogous materials. And then now the way 3D Dirac and Weyl are related is that now you have to lift some degeneracy. You have to break some symmetry. So one possibility is you break time reversal symmetry. The other possibility is you break inversion symmetry. So then you will get Weyl fermions. And if this is topological, then there will be a bulk boundary correspondence. In other words, these Weyl nodes will be connected on the surface by a topological surface state. We'll call that was called Fermi arc. Okay. So then, so one algorithm, experimental algorithm, would be to magnetize the Dirac critical point. That will create a mass in the bulk, but then it will also make the bands non-degenerate, and they cross, and they will create Weyl nodes. And then the other possibility is to make heterostructures where you break inversion symmetry, or just look for analogous materials, crystal structures in the database where the inversion symmetry is broken. Okay, so then you'll get the Weyl emerging out of Dirac, and this cannot happen in 2D because chirality is not a good quantum number in 2D. It's not Lorentz invariant quantum number. Only way chirality is a good quantum number it's in 3D. So for that reason, you can have massless Dirac fermions in 2D, but there is no guarantee that chirality is a good quantum number. There can be a specific reference frame where it's accidentally good, but in general, it's not a good quantum number. So So that's why with graphene type of thing, you never got to Weyl fermion. But with topological band inversion, 3D Dirac, you could get Weyl fermion. This is, in my view, at least from experimental point of view, is why topological insulator gave rise to Weyl, which did not happen with graphene. Okay. Now, there is a long history of theoretical development, how the Weyl equation is relevant for condensed matter. One of the earliest is by Conyer-Sering, who was at Princeton at that time. There's a number of theoretical paper appeared after that. The most recent influential work is by Murakami and Juan Turner Vishwanath and collaborators. They brought the topological insulator connection to the problem. And they suggested some materials where the Weyl fermion experimentally they were not realized. And there are a number of other groups also suggesting materials where this could be found, but it was never found. Early on, shortly after Alfvin's paper, I was also interested. We had a paper in a year later where we suggested that experimentally the easiest way to find it would be to do inversion breaking, look for it in inversion breaking spin orbit materials. And then I had my students and postdocs search in the database, and they identified a number of materials that fits the bill, the algorithm I described. And similar search was also done by other people in China and other places. So what is the main idea? So this slide is kind of summarizing the idea behind, the algorithm behind going from topological insulator to Weyl fermion. And if you like, this is the key theme, key idea of this talk, central idea of this talk. In topological insulator, you have seen that on the surface, you have a Dirac cone. So if your surface, Fermi surface is a circle, right? Now imagine closing the band gap on 2 points. So then in these 2 points, now you have a bulk band, bulk electrons degenerate with the surface electron. Now your gap is closed. You close the topology. So this is one of the earliest questions I asked Charlie Kane, that, okay, if I take a 3D topological insulator, I close the bulk gap, are surface state protected? His response was, it will not be protected in general, because the surface states were protected by the existence of the gap in the bulk, right? If you close the gap, then there's no distinction. The electrons can enter the bulk, right? But there is a way out of that. If you close the bulk in certain ways, then it could be protected, but at that point it was not clear. So we decided to do experiments. We take, as I showed in the last slide, that we take a 3D topological insulator, systematically close the gap by changing sulfur to selenium ratio, where we get to a stage where I have a band inversion, where there's a 3D Dirac. So these are those 3D Dirac points. Now all you do, you either break time reversal by magnetically doping the system, or break inversion symmetry. And in both cases, now Dirac has to split. The degeneracy is lifted. So you'll have a pair of Weyl points, Weyl nodes. And on the surface, and then they're connected. So this is the Fermi arc. So having measured Fermi surface for many years, probably more than 20 years, I did not believe this cartoon, because we have never seen Fermi surfaces that are kind of fractional on one surface, right? It apparently violates many ideas in basic math or quantum physics, right? So I did not believe that, even though this construction looks simple, I did not believe that we will actually see that in experiments. We have to go and do the experiments and see whether there is a non-closed Fermi surface. How is that possible? Okay. So the real materials are, of course, more complicated. It's not like my cartoon, but I will try to give you a feel how that relates to the cartoon. So these tantalum-based materials, if you calculate, these are calculations from my group, if you calculate the surface Fermi surfaces or surface state band structure and correlate with the bulk nodes, Weyl nodes, you see that it has many of those nodes. And so there are two nodes that project here on the surface. One node project here. It's the chirality of the nodes that are the plus and minus denoted by white and black. And then we can also calculate how these how surface states are connected to those nodes. Okay, so then when we do look at the surface, we see a number of these states on the surface, and so now we have to closely examine their connectivity. So how do we know that this Fermi surface, is this a closed Fermi surface or non-closed Fermi surface? What is our test? So one way we can do is that we can look at the energy scan. We can look at the dispersion relation and see whether these states co-propagate or counter-propagate. Let me move forward to show a cartoon first. So if I'm doing a, say, Rashba surface states, then I have a counter-propagating states at the Fermi level. Or if I'm doing a topological insulator surface states, same thing, I have counter-propagating states. The Fermi velocity, there's pairs of Fermi velocity possible. But if I have a co-propagating state, then if I look at the energy dispersion, they should be co-propagating. So only this type of co-propagating states will tell us there's a non-closed Fermi surface. This is not possible with topological insulator, Dirac surface state, or Rashba, or any other surface state. So we have to check in the energy axis whether the states co-propagate or counter-propagate. So we take a unconventional cut. We take a loop cut on the surface states, and we see that in the energy axis, they're co-propagating. They're not merging. And then the fact that they don't appear here is not an image plot issue. This can be repeated. Now, if this is the case, then we should be able to find the bulk counterpart that was on the surface. So what happens in the bulk? Let's back out here. So on the surface, we see states like this, arc-like states, but not so clear immediately. They're non-closed. But if we probe the bulk band structure deep into the sample, then we see that the Fermi surface looks like 2 points mostly. But certainly, it's very different from here. This surface Fermi surface, this is bulk Fermi surface. Now we can image how the surface Fermi surface evolves to bulk or bulk evolves to surface by changing photon energy. So, so one of the things we want to check that if this is our bulk Fermi surface features, then how does it behave in the energy axis? We see that when we do the energy scan, we see these two Dirac-like thing. But when you look at the spin, they are single degenerate states. So in other words, it looks like there is a band crossing, like when you have a band inversion, but then they're somehow split and degenerate. And what is interesting, these 2 points we see are on that, at the Fermi level. Now, so this is what is happening in the bulk. And then now we can put together the surface and the bulk. So this is the bulk, as I just showed. Looks like there are 2 points within resolution. But when you probe the surface, it looked like there's something like this. So in other words, and then we can see that these arcs, where in momentum space within resolution, where they terminate, that's where these Weyl nodes appear. So in other words, the surface Fermi arcs, where the states are co-propagating as opposed to counter-propagating, and they match up to each other within experimental resolution. So here we are putting surface measurement and the bulk measurement together, and we can see that where the arcs terminate, that's where the Weyl nodes are. And we know those are Weyl nodes because they have a spin texture. They're non-degenerate. Dirac would be degenerate, right? Dirac would be 4-fold, and the Weyl node is 2-fold. Okay. So then we repeat that all over the momentum space and figure out how many Fermi arcs are there, how many Weyl nodes are there. And this is our experiment. Now you can see that when I presented the experimental data, I did not refer to any band structure calculation. I could have done that. But so the experimental proof of the existence of Weyl node and Fermi arc, our proof is independent of the calculation. We did not make any comparison to calculation. You can go and try to do calculation, but in the process, we also learned, because we can calculate these things, that since we don't know the surface potential very well for first principle calculation or DFT, you hardly find a real agreement. You'll see some sort of broad agreement, but the real agreement is difficult. So that is the reason I also avoided making a comparison and said that, oh, looks like the calculation, so we found something. So I gave a proof independent of calculation. So this is in the spirit of topology. The topology doesn't depend on the detail. You may not know the surface potential, that may be different. The topological argument should still be operating, it's valid. So the experimental methods, I did not detail on it. It appeared in 2014 in our first science paper, and then we applied that to the tantalum arsenide paper, Weyl fermion paper. In this paper, we already showed that why, from ARPE's point of view, near the surface, the Dirac node could be split. That's because of the cleavage process. So if you like, this was the first paper on. Now that we understand, this was actually the first paper on Weyl, and then this was the second paper on that, and then there are a number of other papers, including photonic crystals, which is fermionic, non-electronic system. So you can call it some sort of bosonic type of thing, and then and all other subsequent work, experimental work, is utilizing our algorithm, how we determine topology, arc and Weyl node topology, without referring to any calculation. Question? Double is like you have a Dirac. Exact double is like Dirac, but then it's split a little bit, but experimentally we don't resolve. Yeah, I mean, it's not a, yeah. So then subsequently, a number of transport works have appeared, including some from my collaborators, detecting some signatures of chiral anomaly and other anomalous Hall effect and all of that stuff. I'm not going to review the transport part, which is a bit complicated. But the fact that we have a spectroscopic proof of Weyl quasi-particles, emergent Weyl fermion in condensed matter, that opened up the field for many other studies, including transport and optics. How much time I have left? Okay. So then I showed you, so as I promised that, okay, so this topological insulator to Weyl, this theoretical and experimental conceptual developments, it opened up many other things. I'll give you one or two examples, depending on how much time I have. So in 3D, it's not only you can have a Weyl semimetal. The Weyl semimetal is not the only possible topological semimetal in 3D, or topological conductor, if you like, as opposed to topological insulator. There are other topological metals in 3D. One possibility is that you have a band crossing like that creates a nodal line, and then there may be spin orbit or magnetism or something, then you can get a non-trivial winding number. And if there is one, then there may be surface states. So this is interesting because if you have particle hole symmetry in such materials, you'll get a flat band, nearly flat band. So here, your topology dictating flat band. We know about twisted bilayer graphene, where the twist angle is creating the flat band, but you could also use topology to generate a flat band. You could think about, what if I introduce superconductivity? Will I get correlated superconductivity, ITC-like thing in a topological flat band? That's one of the visions we had in trying to do this. But in real materials, it's difficult to have very good particle hole, significant particle hole symmetry. In general, lack of symmetry creates some bandwidth on that flat band. So it's a material search issue. But we utilize this idea of nodal lines, interconnected nodal lines, to define a topological magnet that has a topological band structure. So it turns out this type of nodal lines can intersect or intertwine in many different ways, like Hopf-link or inner nodal chain or outer nodal chain. So how do we know these things are allowed? We can write down a model Hamiltonian, and you find that there's nothing forbidden there. Then you go and look in some materials database and see whether this is realized in some material. This is what we're doing. First, we are conceptually defining that we want to find such a thing, and what should be the corresponding band structure, and can we find something similar in a real material? So that is the idea. And so we put forward this idea in this PRL. It's a theory paper from our group, that by linking nodal line, you might be able to find a magnet that has topological band structure in 3D and also operating at room temperature. It's like our room temperature 3D topological insulator, because that's for experimentalists, those are dream objects, right? So here we are trying to find a room temperature magnet that has topological band structure, whose surface will have nearly flat band. So there's a lot of experimental excitement around that. But the theoretical algorithm was laid out here. I'm not going to go over the great details of the actual band topology. As I said, that in real materials, there are many bands. It's very complicated. So I'll sort of conceptually guide you through the data. So what we are looking for is that a nodal line like this, on each node there's a Dirac point or a Weyl point. Either one will do. And then since these are topological objects, they're connected on the surface. So these surface states will create some sort of drumhead-like states, has been conceptually put forward. So then we, as I said, then we found the materials database. We found the materials that fits the bill. It's not exactly what we're looking for, but something close. And we find such nodal crossing by scanning the 3D band structure. With ARPES technique, you can see that when it's crossing, creates a point. Otherwise, so you're seeing this thing here, and here you're seeing this thing. Then you see a dot, and then you see this thing. Oh, so I'm showing on this slide. I'm showing band structure in 3D, kx, ky, and this is vertical axis is the energy axis. And then I'm showing experimental data, kx, ky, and this is the binding energy, you can see. So I'm scanning here. So when I'm up here, this is corresponding to this energy, I see a band like this. This is that. And then when I go subcut, k space, an energy space cut, and then I go down in energy, in this energy axis, then I see here I see a dot. So it's that dot. And then here I see it has opening. Right. So we want to see in these materials, right, what is the band topology? Is there a Weyl node hidden in the band structure? Something, yeah. So we see that there is a crossing. So in other words, there's a zero mass object in 3D. So it's a Weyl node in 3D. So then this material has many bands. We do that on all these bands that this material has, and we explore all these details. Where are the Weyl points, and where are the loops, and where are the surface states? So this is one example of that. So I'm showing kx for particular ky, and then the energy cut. So this is based on DFT. We expect that if I go to ky value like this and scan kx and energy, then I'll find a Weyl node here. And then we can track that in ky by changing ky, and this is what we're seeing. So in other words, there is a Weyl node loop in this 3D Brion zone. Yeah, in this compound, I'll show that instead of hop, we are finding chain link. The hop link is not realized. That was in theory, but in experiment, real experiment is the potential is never the same. So then here we found that it's like nodal link rather than hop. Yeah, I'm coming to that. So then we can probe, we can isolate the bulk band structure and the surface band structure by probing their kz dependence. If something is not kz dependent, then it's surface. And if something disperses in energy in kz, then I know it's three-dimensional, right? I can probe that. So based on that, we identify the signal here is coming from the surface. Here we show that kz dependence, that as I change kz, that signal doesn't. So this signal corresponds to this thing. So in other words, these line nodes are connected by these surface states that are drum head-like. It's not completely flat, but there is about 100 millivolt bandwidth, which is really good, given that it's not a strongly correlated material. Okay, so now, all of that is RPES, mapping out the Weyl node and all that. And all these Weyl nodes will contribute to transport. So now we are trying to see what we measure in spectroscopy. Is that a crazy thing, or there is a connection to transport? So one thing we can do, we can take the RPES band structure, these 3D Weyl nodes and loops, and optimize the DFT, because now I have the parameters from the real material. And then once we do the optimization, then I can calculate the Berry curvature field, kx, ky, Berry curvature field. And then now I can calculate transport properties, because the Berry curvature field is related to anomalous Hall effect, intrinsic part of the anomalous Hall effect. Also from experiment RPES, we know where the Fermi level. So then we know that this material has Fermi level here, and the Berry curvature field calculation requires knowing the Fermi level, how much you integrate from where to where, right? So we do that from a real material. When we do that, we find that based on RPES, we predict that this compound, if someone does transport measurement, this compound should have anomalous Hall conductivity on the order of 10 to the 3, little less than 10 to the 3 standard units. So in other words, it's here. And this is, there's a near divergence here, because then you hit some Weyl point. Weyl points are singularities of Berry curvature field, right? So we see that we are below the Weyl point, so you should not hit the singularity. So then we predict, based on spectroscopy, we predict that the transport should have a value in that order. So in this particular case, the transport was carried out after we predicted what is the intrinsic anomalous Hall conductivity. So when we extract the intrinsic Hall conductivity, anomalous Hall conductivity, it's 870 standard units, and it's pretty much right in the right ballpark. It's a remarkable agreement. So the reason I show is that spectroscopy has reached a point, it has advanced at a point that now we can take all these relevant parameters and predict transport, not only just image topological order, topological invariance, we can also predict transport. And in the historical sequences that people would do some transport and then spectroscopy, try to do some spectroscopy to figure out the microscopics, what is happening in the system, why transport is the way it is. Here we are now reversing the direction, that the spectroscopy has advanced so much that we can predict certain types of transport. This is not just one example. We have more examples. I don't have time to get into that. 1 minute? Okay, I'll take a minute. Thank you. So, so this is my final 1-minute topic. So what we have seen so far, these Dirac bands, massive Dirac bands or Weyl points, all these things create unusual transport behavior, or optical behavior, right? So then here we were motivated by the fact that can we find materials where there is Dirac physics, Weyl physics, massive Dirac band. You know, in the last example, I was searching for a flat band so that it has strong correlation, many body effects, right? So it turns out Kagome magnets are ideal for that. Even just by the lattice connectivity, lattice network, you have both Dirac fermion and flat band, right? Now, if you have magnetism, especially out-of-plane magnetism or some component of out-of-plane magnetism, those Dirac fermions, that time reversal symmetry will be broken. You'll open a gap. So in other words, you'll have a natural topological magnet realized in a Kagome magnet. And if you lower your chemical potential here, you'll find flat band. You don't have to go to the drumhead and nodal loop states, right? So for that reason, searching for Kagome magnets could lead us to interesting new physics. So this is one direction where you could spontaneously, naturally realize. In the first example, I showed so much materials and band engineering to realize a Chern gap magnet. Here, it might just spontaneously, it might already be there in the material. And same thing here, the flat band could be there. So, so we probed this system with our STM measurements, and I'll not go into that, but I'll tell you that now we reached a point where it's not described by conventional topological theory anymore. We're starting to find things where we're breaking out of that paradigm. So far I gave you a number of examples: topological insulator, Weyl semimetal. There's a standard theory framework. What was lacking is that can we find a material realization and see that? Now we are reaching a point, we are taking off to a direction where we're finding things that are not falling into the paradigm. So this is one example of that in this Kagome magnet. You can see the Kagome magnet has 6-fold symmetry, lattice, right? So then your electronic states, or your electronic structure should be 6-fold. But what we see, since the time is short, what we see that it has a 2-fold symmetry. So that reminds you of some sort of nematic order. And nematic order is not new. It has been seen in superconductors or other correlated electron systems. It's a signature of strong correlation. But not only that, what is new here, unprecedented, is that here, in this case, we can control the nematic order direction. So we apply, this is without any field, B equals 0. Here, when we apply a field in certain direction, we can see that we are controlling the nematic axis. So that is unprecedented. No other correlated system we know of where you can control with a modest field, or any field, you can control the nematic order direction. And then when you apply a strong out-of-plane field, your 6-fold symmetry recovers. So then there's some sort of phase transition happening into this correlated state. And then you can, not only that, you can also reverse the direction. So this is, in my view, is the first example in topological materials where we are breaking out of the theory paradigm. We don't have a clear-cut theory how to model this system, what is happening, because now strong interaction is involved. So it's an example of many-body physics in the presence of a topological system. So there's another puzzle about this system that, as I showed, in the Chern magnet, 2D Chern magnet or topological magnets, if we apply a field, then the gap opens, and the larger the field, the gap is larger, right? Here we see that there was a gap in the unperturbed material. There was a gap in the ground state, gap in the band structure. And then when we apply a field, we see that the gap, when we apply a field, then we see that the gap is actually decreasing with the applied field. So it has this additional twist. So this is something we don't fully understand. But what I argue, I would like to leave with that not only we have now good control of topological states of matter, how to realize them, how to manipulate them, at least at the spectroscopic level. The next future direction is to achieve similar or finer control in a transport setting, and all this, and optical setting. All these things are beginning to happen. And another exciting frontier is to consider superconductivity in Weyl systems. Let's say if two Weyl fermions pair form a Cooper pair, what type of topological superconductivity you could realize. So many of these things will be explored in experiments. I think there's a very exciting time ahead. So this is my last slide. So when I started to teach at Princeton, that was what I was teaching, that this is condensed matter physics. You have these phases, and these are phases and phase transitions. But I had very little clue and almost no clue that 15 years down the line, I'll talk about things that just did not exist in the field. So I think there's a very exciting development that has happened in the last 10 years, and the entire community working on topological insulators have tremendously contributed in advancing the field. Thank you.
Have you analyzed the Plato Hall effect on surfaces? Of course, but